Alright, so welcome everyone. In the previous lesson, we discussed about the important fluid emitter sections, the properties and the attributes of the fluid emitter. Now in this case, we would like to go for the fluid container node and the important properties. So first of all, let me just open up with the attribute editor. So here we can see that we need to, of course, we need to enhance the resolution of the fluids. Well, for this complete reaction, I took the base resolution of 135 to 150, I guess. I think it was 150, yes. And the final resolutions at the end of the frame 120 was somewhere around the size on the X was, I guess, 400, and the Z was approximately 420. For the Y-axis, it was still 225. Okay, so there's really going to be a good resolution which we have to use. But for the initial, I like to go for the 60, which is a very decent value for the base start. Okay, so let me just put that thing to the 60, and of course the size are already set. We don't need to work upon here. And for the boundary X, I would like to go for the none. For the boundary Y, I would like to go for the minus Y, since I don't want my fluids to go beyond the base. And again, for the Z, I like to go for the none. Okay. Now coming to the content method, as we can see, we would like to go for the density and velocity, these two grids, only the dynamic grid. Since we have already discussed with you, there is no usage for the temperature and the fuel for this particular reaction. So I just don't want to consider the temperature and the fuel. So the default, the density and velocity will going to play a perfect role here. So both set to the dynamic and the dynamic for the density and the velocity. All right, coming back to the display, what I can do is that, just to avoid this, the visuals of the voxels or the container, what I can do is that I can just go to the boundary draw. I can switch to the bounding box. That's again good. And now for the dynamic simulation. Now guys, pay attention over here. This is really going to be important as a soul for the reactions. Okay, so let me just start with this first step by step, and with every attribute an explanation why we are using this, which is really very important. So while simulating the dry ice effect, I have noticed one thing, that there is a very less difference between the dry ice smoke and the wispy smoke. If you're going to take a look at that carefully, you will see that the dry ice is also, contributing certain properties and parameters of the wispy smoke, at least in look and feel. Of course, the wispy smoke rises up and the dry air smoke rises down because of the reasons we all know. But for certain degrees of extensions and for certain degrees of look and feel, I can correlate somewhere somehow the dry ice smoke and the wispy smoke. So in this case, I would like to take the advantage of the viscosity to take my dry ice smoke to be a little bit wispy in the nature and to be a little bit stretchy. All right, it's not going to be like that, a completely a very hot smoke that keeps on expanding. No, it'll do, but not in like that fashion. So the viscosity here is really going to be very helpful. But just an important note here also, do not extend this value, otherwise your fluid will get stick and they do not move because of the high viscosity values. I did that thing and I came to know that the high viscosity was responsible for that. So what I'm going to do here is that maybe I can go for 20, and maybe I can go for 0.015 also, but I guess 0.020 is a good start. Okay, we're not going to use the friction over here. For the damp, is very important to give the rest to the fast moving fluids, as well as just to have some more sustainability of the reaction, or to make the fluids a little bit more calm. So I'm going to use the damp, so that for every frame it will going to bring down the velocity of our moving fluids, a decrement value of 0.020. All right, now solver is going to set to the Navier-Stokes, which are perfect for simulating the gas and this kind of effects. High detail solve I like to consider, of course, I like to go for the all grids. since the reason why I'm using the hydrogel solve is clearly apparent, because hydrogel solve is always try to add additional details by conserving the mass and the velocity of the fluids. So if you do not going to use the hydrogel solve, you may could want to crank up the resolution of the fluids to fairly high value, which is sometimes good also. But in my situation, the hydrogel solve is on because I want the dry ice when it keep on moving, the mass when the advection is taking place, which means that the fluids which are moving, they are carrying the mass, they should also conserve the mass. So that's for the reason I'm insisting the hydrogel solve should be considered. All right. Now for the sub steps is also very good important. Reason why? Because I will later going to tell you up that we're going to utilize something called the density pressure. So many times I've noticed that the density pressure always try to break the fluids, sometimes into the jitters and all. So just to avoid that, we like to go for the sub steps, set that thing to the 3. Okay, that's pretty much fine. Now for the solver quality, I like to go for maybe 60. The reason why I'm going this because I want the dry ice to be a little bit more incompressible, so that when the dry ice will fall upon each other, they just try to get pressure, and they try to push themselves a little bit forward. So I think so solver quality 60 will going to be a good start. The simulation rate scale is obviously going to, we're going to leave that thing to the 1. That's really not going to be a problem because I don't want to have a high value of the simulation rate scale that's going to make the fluids, unrealistic. So 1 is going to be the good start. Okay, so for the next, I'd like to go for the forward advection now. This is again a really, really, very helpful option in my opinion. Well, you know what? Sometimes I tend to observe that my fluids they show some static fluid problems. By the mean by the word static, what I mean is that when fluid just whenever you try to give them some certain amount of the pressure through the temperature pressure or to the density pressure, I have noticed that some of the voxels after getting released through the pressure, they may could get stable or stuck inside the voxel grids. So the forward advection will also going to push the fluids towards along the direction of the moving fluids, and this option is really going to contributing the dry ice simulations to move forward. I also going to show you up that what exactly is the use of this. Without the forward advection, it's almost impossible for us to utilize the certain properties of the fluids, which is the density pressure and the ammeter turbulence. So the forward advection here is really going to be very important. Of course, I'm going to keep the evidence substeps to on, so that I also want the it will going to calculate in the substeps, which is again a refinement of the fluids. And of course the auto resize is very good important. We will use the resize to emitter, and be careful in switching off the resize closed boundaries, otherwise there will not going to be any use of keeping the boundary set to the none or to the minus y axis, which was we considered the boundary minus y. Okay, so the max resolution will going to exceed somewhere around 400, so I like to go for the 400 to be on a safer side, because I've experienced that at certain frames I've noticed that these grids, the containers generally got stopped because the base resolutions was beyond the max resolution. So I don't want to use that. So the max resolution I would like to prefer for 400, or maybe you can say 450 will be better. Okay. Now for the auto reset threshold, I would just want to go for the 0, and the auto reset margin like to go for the 1. That would be fine. Okay. So I guess these are all the necessary settings which we did to enhance and to create the dry ice. We're going to have more settings of the density and the velocity in the next lessons. All right. So stay tuned.